So in this video, we're still in section 14.7, and we're going to solve a problem that is described as finding and classifying the local extreme values of a given function. Z is equal to f of xy. And I wanted to look at this example here. And we know that to do the local extreme values, it comes down to two different steps. You need to first find the critical values. And then step 2, we need to do the second derivative test at all these critical values, however many of them there are. Okay, so let's go ahead and do the first step first. I'm going to define this function to a function of two variables, and you can I'll leave you to show the answer to this problem by hand, but if we have function 2x cubed plus 2y cubed minus 9 times x squared plus 3 times y squared minus 12 times y. Let's make sure we've got that typed correctly. 2x cubed, 2y cubed, 9x squared with a minus 3y squared, correct, and then minus 12y. First thing to do is to find the critical values, so we want to solve, and we want to take the derivative of the function of two variables. So we're going to first solve the derivative, and which derivative we want to take is the first derivative of the function with respect to x and y, so there's the gradient. Set that equal to 0, and we want to solve for x and y. Okay, and making sure that close off my parentheses, and you can see here that according to this solution we have 4 critical points. Okay, we have 4 critical values of this function. So what we want to do is run the second derivative test at each critical value to figure out what kind of critical value it is, a local maximum or a minimum, or a saddle point, or maybe the second derivative test comes out to be inconclusive and we might need to resort to some other method to figure out if you have a max or a min or whatnot. So let's continue with the next step. We have, again, that same function. I'm running the demo that I've written for this purposes of demonstrating the second derivative test. I put in the same function that we just put in, ran this program, and it tells us these critical values. And I've chosen to do the second derivative test at one of those critical values. Okay, so I picked a point of interest to be specifically one of these critical points. And now we can see here that if you were to, can you see that at that point the gradient comes out to be equal to 0, and the Hessian at that point comes out to be a negative 18, 0, 0, negative 18. And if you can think ahead to what this is going to mean when you take the Hessian and multiply it by any vector, right? The fact that there's a negative 18 and a negative 18 here and zeros everywhere else, what that's going to equate to is you'll have to get the discriminant or the determinant of the Hessian, and you'll have minus 18 times minus 18, which is a positive number. Okay, but the second, so d comes out to be positive, but the second derivative with respect to x is negative, which tells me that this function should, in various directions, be opening downward. So if we look at a plot of what that happens, we can see here that in any possible direction, because fxx came out to be negative and d was positive, this function is going to open downward like a parabola in every direction. Okay? And this tells us that if we check our local max-min problem, that at that particular critical value, the function is going to look like a quadratic or a paraboloid opening downward. Okay, Now we know that there were some other critical points. There's another critical point, 3, negative 2, right? So if we put in that 3, negative 2, that point of interest, and rerun the program, okay, we can see that something interesting happened. Not much changed, except something very subtle, that fxx came out to be a positive number. So you're saying, okay, well, the second derivative test says that fxx is positive, that we're going to have the function opening upward in every direction. Accept the fact that fxx alone is not enough to determine the local max-min. You also need fxx, and you also need the determinant of the Hessian at that particular critical value. So when you take a positive 18 multiplied by a negative 18, d comes out to be a negative number, in which case at that particular critical point, 3, negative 2, we're going to see something that should look like sometimes the function is going to open up, and then because of that negative in the Hessian, sometimes the function is going to open downward at that point. So we should, when we look at a plot of this function near that point, see something that looks like a saddle point. Now, what's going on here is this is only a local picture. We're looking at just the function near the point, near the critical point. So all we can do is try to piece together what the full graph looks like from the larger picture. There was two other critical points. You can look and see what they are, 0, 1. So let's put 0, 1 in for x and y. We've got another critical point. We can rerun our code. Okay. And again, we can see that fxx comes out to be negative, but what really matters is that d comes out to be negative. And whenever d is negative, whenever you take this determinant, you'll get negative 18 times 18 minus 0 times 0, which is a negative number. Whenever d comes out to be negative, that's enough to indicate that your function is going to look like a saddle point. Now this is what the function looks like near that particular point, only locally, only near that point. Okay, so let's go ahead and create a nice picture of this function, realizing that we've got a couple saddle points. Okay, I'm going to put this into different plotting. So let's plot explicit functions. Actually, let's use the one right here. Okay, so let's go ahead and create this plot, put in this function, and let's create around a point. Let's see what this graph looks like. Okay, and you can see here, let me see if I can bring this into focus a little better, that this function looks pretty crazy. Let me make this a little smaller so it all fits on the screen at the same time. Okay. We can see that there is a local maximum. Okay, one of the critical points was this local maximum here, that as you move upward in this function, we're getting to a point that is higher and higher and higher. So the contour plot, we're seeing that as this little circular region. There's also another circular region here, but it's on the back side of this function. Okay, so that looks like a local minimum at this other critical point, which is at the center. If you change the number of contours, right, we can see that we're getting something that looks like these two mountaintops, except one of them is that little valley. And then you can see right here, these 2 points, this is what a typical saddle looks like. It looks like this kind of X shape. And we've got 2 X shapes. You can see them kind of starting to form right there. Maybe if I throw in a couple more contours, you'll start to see this X shape forming more clearly. That corresponds to the Let me move this contour down so you can see the saddle point. One of the saddle points is right there. That'd be a nice place if you're out hiking or camping or something, just to put your tent right there, and then you can hike out and up in the morning, or you can hike down to your car if you wish. So at a saddle point you can go up or you can go down depending on the direction. So that is a full harder example that has multiple critical points, and we found all 4 of them. So that's what we have: 1, 2, 3, 4 critical points.